All right, so a brief description of the syllabus and the way we plan this course. Maybe first of all, about the grading and the workload. We'll have 3 homework assignments that are based on Python notebooks. We will maybe talk about them a little bit more at length tomorrow. We'll have a quiz towards week 4 when you start actually working on your final project. So we don't want to give you another assignment, a programming assignment, but we'll kind of have a quiz about the materials that we will cover towards the last 2 weeks. So this is a 5-week course, right? It's a summer course. So this is why we have homework every week. Starting this week, you can start doing this. The submissions will be the Wednesday the following week. And the final project that we will publish some prompts or some ideas. Could be a group project. We'll have kind of to check with you and get some project proposals if you don't want to do the prompts, or if you have questions about the prompts and how you get organized in the group. But that's kind of pretty much the structure itself. In terms of the schedule, so it's actually broken down by classes according to the session, to the summer session. So we have basically 5 weeks, and we have 4 classes: Monday, Tuesday, Wednesday, Thursday. So that's pretty much the plan per class. And as you see, it has quite a lot of material. Today we'll talk about representation of sound and music, basically the basics of data, because the whole concept is, well, how we can use machine learning either in more traditional ways or the deep learning aspect, and build machines that either understand music, can generate music. We will be talking less about music information retrieval, which is a field that is pretty hot, which more deals, as the name implies, with retrieval. My main interest personally is in creating systems, generative systems, and systems that can improvise or create new music. Some of this could be synthesis, some of this could be generating notes. And the applications are varied, of course, from creative musical tasks like computer-aided composition, machine improvisation, which is a field that I was working on a lot. But you can think also about anything like adaptive music for video games, or just systems that can generate audio or music in ways which are adaptive. We'll talk a little bit about speech. I'll get to this when we talk about the syllabus. Although this is more part of an audio, speech synthesis is a whole field of its own. We have some students working, some graduate students working on singing synthesis. So this is kind of how do you make an expressive speech synthesis that can actually sing and not just talk. But we'll kind of just give you a notion of what is, also how you produce speech, which is slightly different from the way you would treat musical notes. So the first part is really what is the basic data. And we'll talk about 2 main representations today, media and audio. And this would be, we're going to just hopefully cover the basics, so we kind of understand actually what is the domain, what kind of data we're looking for, what kind of features we can extract. And I'm talking about the traditional features, not machine learning features. So feature representation will be later on, starting week 3, where we start talking about machine learning. And not machine learning, but deep neural networks. I mean, everything is machine learning here, but mostly talking about the representation learning aspect of deep learning, which is one of the more powerful aspects of machine learning today. So once we cover the representation, the features, both in terms of symbolic and audio, we'll jump to talk about that generative part, which I'm mostly interested in. And this is how do you create music from something? So what is that something? That would be maybe a random process. So one of the underlying ideas, because it's mostly about generative applications, is that you take a random number generator and you want this random number generator to create something which resembles a real example. You can think about this in some sense as a deep fake of music. But the concept itself of using random processes, which you call aleatoric or stochastic, and I'll talk about this tomorrow, has been prevalent in music in general. Some of this was more experimental. And today, I would say, to generate music, the underlying model is a generative model that has this inherent statistical representation, or there are these latent spaces that generate random numbers, and the network actually can turn them into reality. So from noise to image, from noise to style imitation. But the concept itself will introduce very much talking about the Mozart dice game and some other composers, and then talk about ideas of randomness that are related to complexity in music and a field that is called music information dynamics. So kind of introducing the concepts, but it's conceptual shift from the data to basically some underlying models of music. And this is in contrast maybe to traditional AI that was based on writing rules, maybe grammar based, maybe in some other ways, but the trends in AI changed. So of course there were other ways of people trying to do AI and music by writing expert systems. So we will not be covering that. We'll be basically talking about statistical modeling and learning statistical processes. Then we'll jump a little bit deeper back into the theory of signals and actually look at a little bit of a digital signal processing. I mean, this is a CSE class. Usually, DSP is a field that electrical engineering covers better than CS. In my background, my master's was actually in electrical engineering, and I was teaching signal processing a lot. And of course, acoustics and music are closer to signal processing in some sense than what you would normally study in computer science. So when I was doing my PhD, I was actually moved back to computer science, but I had the signal processing background. And so for those who come from computer science and have not dealt with signals, we're going to talk about, it's going to be a little bit mathematical. We'll talk about basically how do you take a signal, an audio signal. I'll mention this today as well, but we'll not talk about sampling or how do you turn the signal, an acoustic signal, into basically a digital file. But once you do this, you start analyzing this in more formal techniques. So we'll talk about spectral analysis. We'll actually mention them even today because it's almost impossible to talk about music representation without talking about so-called the frequency content. So Fourier transform, spectral analysis, but then, the convolution and the filtering aspect are really kind of core ideas of digital signal processing or electrical engineering aspects. Once you talk about signals and systems, you have to understand these concepts. And since we're dealing with audio, this will be kind of a 1-hour crash course on signal processing, digital signal processing. We'll continue because this is actually, it's not just 1.5 hours. Wasn't able to fit this in one class. So we'll have, Wednesday and Thursday. This will be your electrical engineering crash course, because we'll talk about short-time Fourier transform. How do you take a signal, represent this in frequency using this Fourier transform, and then how you invert it back, something which is the basis for a lot of audio manipulations like phase vocoders. What are the conditions for going back and forth between frequency representation and time? So these reconstruction rules, and a very important aspect that anybody today doing deep learning, let's say in speech, hits this Griffin limb technique. And we'll talk what it means, phase reconstruction. Actually, once we go and we analyze signals in terms of frequencies, there will be this notion of phase that is often lost if you want to learn something and then you want to generate new structures, new phonemes, new expressions, or new notes, we usually look at one aspect of this Fourier analysis, which is the amplitudes or the energies of the different frequencies, but we ignore something that we call phase. So for those who haven't heard these concepts, I'm throwing a lot of a lot of terminology, but since many times phase is lost, we need to reconstruct, and Griffith limb is one of the methods to do phase reconstruction to invert these frequency representations, the short time Fourier analysis or the spectral analysis. Oh, sorry, I jumped back to where is our syllabus? Yeah, to generate an actual signal that we can listen, we have to reconstruct the phase. So as I said, like the first week, if I can summarize, will be, just the basics today, more setting up the whole framework, the problems, the domain of machine learning in music and audio, and then a little bit of the electrical engineering aspect of it. The second week will actually go deeper into this idea of noise or probabilistic representation of data. And again, information theory is something that you will encounter in your machine learning classes. We didn't require any machine learning prerequisites for this class except for statistics. But I mean, class about information theory is also usually done in electrical engineering. So somehow this is really, a lot of the materials we'll be covering are covered in ECE. So we'll talk about information theory in music, concepts of probability, entropy, or uncertainty or complexity of data, and then some ideas of compression and ray distortion, because now we'll kind of formalize these ideas that you can turn noise into structure, or maybe go the other way from structure to noise. So compression is actually an attempt to take something and represent it so efficiently that you cannot compress it anymore. And if you cannot compress it, then you cannot predict and cannot find any structure. It's actually noise. So you can think about this duality conceptually of going from structure to noise and from noise to structure, either as an idea of generating something or an idea of compressing or finding an efficient representation. So there is a close link between machine learning and information theory in that aspect. So we kind of introduce these concepts, and that will be a little bit of a theoretical aspect of the statistical or the information theory aspect, how it's related to music. And we'll continue talking about how to generate things from randomness. We'll talk about Markov models. We'll talk about using compression algorithms like Leibniz and how you use them to create sort of a code book or a tree that represents your music, and then how you can actually generate new music from that compressed representation. So the first three classes are the statistical aspects, mostly symbolic music. And we'll go back to talk about signals and mostly about speech next Thursday, where I'll introduce the aspects of signal modeling that relate to so-called formants, which are the way we produce the phonemes and the vowels mostly in speech. So we will want to use and explain this as well, because it kind of gives us a natural introduction to so-called hidden Markov models that exist in other domains, but they were very much celebrated in speech recognition. To understand HMMs, which are also useful for music, but somehow the speech is the canonical way of thinking about these Markov models and some acoustic models as a mechanism that can create speech. So kind of that logic is, well, we introduce the probability here, we introduce a little bit more specific aspects of audio features here, and then we combine them in the beginning of week 3 when we mentioned hidden Markov models and a so-called expectation maximization algorithm. Again, we're not going to give all the proofs, and it's impossible to do so much in so little time, but we'll kind of give the main ideas of these methods of how you estimate these models. And the practical aspects, yeah, we'll show you or point you to a lot of existing frameworks, toolboxes. Again, we'll be using mostly Python that implement a lot of this stuff. So, of course, I would recommend then whoever is taking the machine learning track to go and actually, follow the classes. I think they're actually required, and learn the proofs or go into the more detailed math. I'll talk about variable Markov Oracle, which is a lot of this is my own research with a lot of collaborators and students and other researchers. So this is kind of a Markov model that relies on string matching. A little bit combines aspects of that Lempel-Ziv compression that I mentioned somewhere before. Yeah, here in class 7. So Lempel-Ziv is a string compression, or well, it is a compression algorithm for strings, for symbolic strings, and the Markov Oracle is based on another string matching algorithm. So we'll talk about this. These are really implementations for machine improvisation, and music information dynamics will be a little bit more formalized here. Then that's Wednesday. This will be our big jump into the field of deep machine learning, deep neural networks. So we'll introduce neural networks in general, how they're related to music, and we'll talk about autoencoder and feature learning or feature representation learning, representation learning or feature learning. And we'll kind of spend some time talking about these autoencoders, variational autoencoders, the evidence lower bound, which is a principle that is used for learning them, and show how they can be applied for analysis of either generating music or detecting chords. And from here, we'll focus really on deep neural network models. So, as I said, it is like a tour de force. I mean, we cover so much. So this is why also your feedback and knowing that you feel comfortable with understanding what these networks do and how to use them will be important for us to keep in touch. So recurrent neural networks, or RNNs, are very powerful models, sequence-to-sequence models or combinations of these things. Then we'll talk about GANs, which is really a hot topic, generated adversarial networks, and ideas taken from so-called peaks-to-peaks or some other cross-model learning, or learning that actually takes two types of data and learns the relations between these types of data to be able to generate new credible data. So if you think about this as sketches, so you can sketch something, and then the computer basically creates a photorealistic image for you. I don't know if you've seen these peaks-to-peaks things before. There's some very cool web applications that actually demonstrate these things. You can also create scenarios like, instead of doing graphics, you sketch a street, you sketch a building, and it will actually create for you, like not exactly fill in the texture. It will actually kind of alter that image a little bit and actually make this really look as if it was a photo. So if you think about stuff like that, going from partial information to complete information, we'll kind of explore some examples, like going from chroma representation that we'll talk about today to actual music. Chroma is very partial representation. It's a little bit like chords. So if you give some sort of a structure, how you can actually generate a musical piece in a specific style just by specifying something very partial. And this would be really more advanced topics like the transformer, attention, which is part of RNN idea, and transformer is actually sort of all you need is just attention, musical form, predict information, which is an extension of information theory to time processes. So this is really kind of introducing it, more advanced topics. And as I said, a lot of these, I guess you'll be jumping on for your projects, because I think this is the hot topic today. I think everybody wants to do deep learning, although frankly, the older models still outperform for many tasks. So this is why it's important to actually to know both of them. But there are all these networks that are worth learning, and of course the more traditional methods. And so I expect you to kind of be practically using these. These will be more advanced materials that we will kind of focus the quiz about, and we'll have week 5 for project presentations and discussion. And since we have I know over 40 students, we'll see how many, we will group you into 3-4 people in projects. So we still want to have enough time. If frankly all we have is what is it, about 6 hours, a little bit less, right? It's four times an hour and 20 to go through the projects. So we want to have everyone have a chance to present their project, and then we'll also publish the requirements for the final report. So we'll have project presentations in class, and then you'll have to submit a final write-up that summarizes this in a sort of a toy paper format. It'll take some kind of a format like NIPS or some other conference where you will summarize your project. This is more common maybe to graduate classes, but this is kind of where we were thinking about trying to do these things. So these projects, even if they will be more of a capstone projects following our prompts, you still would like you to summarize and give some background and description of what you did. This is pretty much what I wanted to show about the class. Let me try to stop sharing and see how I actually get also stop recording. So we'll have, all right.